Okay, so good afternoon, everybody. My name is Fabio Pizzati, and I'm here to present a paper leveraging local domains for image-to-image translation. This paper is a result of a collaboration between INRIA, VISAPP, and the University of Parma. I'm second author, Anthony De Leva is the first author, and we are both PhD students by Massimo Bertozzi and Raoul de Charette. Okay, so the whole paper is about image-to-image translation, which is a task that is typically accomplished by using generative adversarial networks, so GANs. Let's suppose that we have a source domain that we call X and a target domain that we call Y, where with domain we identify some set of characteristics which are common inside a dataset. For instance, we can have the daytime domain and the nighttime one. The task of the image-to-image translation network is to somehow transfer the style, translate the target domain style onto the source domain images context. And so as you can see here in the example, we have a daytime image here on the left, and we can modify its style, make it resemble nighttime without modifying the scene context. So the scene remains basically the same, as you can see the structure here. Okay, so these kind of networks are pretty well known in the literature, also because they are pretty useful for transfer learning and domain adaptation. I'm talking about some kind of technique in order to adapt the task networks. For instance, let's suppose that we have a semantic segmentation network trained only on daytime data, like this one, and we know that if we switch to nighttime inference, this performs really bad. So what we want to do is to translate the input, and then in this case, we can adapt a robust inference into nighttime. So we translate the input, source domain input images into nighttime. And this is just a basic technique. There are others which integrate image-to-image translation networks inside domain adaptation strategies. That being said, there may be problems in using image-to-image translation network for these purposes. So let's suppose, for instance, a training in which we have source images and target images which are structured like this. In source, we have highway scenarios which are typically highly structured. So what we notice inside highway scenarios is that we have, for instance, the lane markings which are perfect, like without any damaging or problems. Instead, in unstructured scenarios like the one here at the top, what you can see is that the lane markings are always missing, like often missing or damaged. So what happens if we train an image-to-image translation network in this setup and then we use it to infer and translate these images? Well, the results are not so satisfying. So here you can see an example of the translation. And as you can see, there is a significant difference, even if the global context is indeed modifying. So the scene is changed in terms of color and appearance, but there is a significant difference that the lane markings are not impacted by the transformation. And this makes these kind of images not suitable for transfer learning. Let's suppose that you wanted to perform well in a structured scenario like these ones. There is a significant difference which is impacting the thing. So what we think is that there is some kind of problems in this kind of network to identify which is the context to translate and what is not. Our proposal for this is to hallucinate new domains. So let's suppose that we have the source and target domain that I was talking about, and we try to train a state-of-the-art image-to-image translation network. Well, what is happening, as I've shown you before, is that the I2I network is not working correctly. There may be also another problem, that is the target domain images are not available. This because, of course, these kind of images may be difficult, challenging, or impossible to collect. For instance, if we talk about images with damaged lane marking, it's not so easy to identify them inside the street. So what we propose is to hallucinate a new domain that we call X prime by using only information in the source domain. So we train an image-to-image translation network only on this set of images, and we want to hallucinate a new domain which is more similar to the target domain, which is unseen for us. So being more similar to target, in this case, these images would be suitable for transfer learning purposes. Okay, so now I'm going to introduce the main idea of the paper. We, as humans, know more or less the structure of for instance, a street. So we know that in the street we have markings, but if we move towards the left or to the right, we may find only asphalt. That's because the street is structured in a given way. So we want to exploit this knowledge. What I'm doing right here is exploiting some guidance which comes from human general information. So the idea is to adapt a new strategy of human-based machine learning and putting again the human in the loop and not just only relying on data. So we want to exploit geometric guidance based on human information, which have more information about the context and the scene which are represented. For this reason, what we do is introducing local domains. So a local domain for us is a spatially identified subdomain. So let's suppose that we have a source domain which is highway. Inside highway, we can identify two domains, for instance, the marking domains and the asphalt domain, because all share a particular information, being having a marking or having only asphalt. And this is also happening for other scenes. For instance, in snowy scenes, we know that, for example, there may be regions in which we have snow and regions in which we don't have snow. For instance, sidewalks and main road, because the sidewalk is usually not clean, while cars and trucks passing on the road usually melt the snow. Or, for instance, we can have foggy scenes in which we know that there will be regions closer to the vehicle which have no fog, and regions far away which are foggy indeed. And moving away from autonomous driving, we can also consider DSLR photography, in which the foreground is often in the middle of the scene. So we know that that part will not be blurred, while in the corners we will have some kind of blurring effect. So our proposal is to train image-to-image translation network on local domains. So let's suppose that we have a training image here, and we have a couple of information that we exploit in order to extract local domains. For instance, here the lane marking masks. What we do is extracting patches relative to the local domains that we are identifying. For instance, marking and asphalt. And doing this operation many times, we can crop two local domains, namely X beta and X alpha, that we identify as source and target dataset to train our image-to-image translation network on. This is very important because we have also, by default, patch-based few-shot capabilities. What I'm meaning with this is that we can extract a single marking from any image, but we can also do a multiple patch extraction from this same image, multiplying the variability of our training dataset, because we can extract as many patches containing the local information that we want to exploit for the training as we want from single images. So this method will be inherently few-shot. So I'm going to show you the complete architecture for the training. So let's suppose that we have a source domain that we call X, that may be few-shot, in which we have images and some kind of information that is used to exploit the local domain. Again, this information is this kind of mask, which is semantic mask in this case, is not mandatory for many translation. Like, the important is that we exploit some kind of human idea in order to extract geometrically guided patches that we call local domains. Okay, so in this case, we extract a local domain which is with marking and a local domain which is without marking. And what we do at this point is to train an image-to-image translation GAN on these local domains. At the inference step, what we do is to translate one of the two local domains. For instance, here we are translating the images with marking into making them resemble images without marking, like in the example here. Okay, at the end, what we do to hallucinate the novel domain is simply compose the generated images with the source ones, we're using traditional computer vision operation, and getting this kind of images which are closer to target, in this case, unstructured scenarios without lane markings, but starting from a source domain, which is highway. So this is completely novel. So we went a little bit further in the paper, and we wanted not only to perform a realistic transformation between local domains, but also a realistic evolution. So in this case, we asked ourselves what happens if we, instead of having just the transformation between with marking to without marking, we also want to perform a realistic evolution from local domain with markings to local domain without markings. Because we know that, for instance, lane marking, this is just a particular example, we know that lane markings can be particularly damaged and not only disappearing. So in order to do this, what we do is to train a local domain variational encoder-based interpolation strategy. So our idea is to extract the same knowledge that we have about the local domains, not only on images, but also on the assisting mask that we use for the task. For instance, let's suppose that we have the mask of the X domain here, and we can exploit our human interpretation of the problem in order to extract local domain on patches. So in this case, we have the local domain on the patch with marking, so P beta, and the local domain of the patches without marking, so P alpha. In this case, what we do is, instead of training an image-to-image translation network on this, we train a variational encoder. And why we do that? Because we know that variational encoders are used in order to encode information inside a hidden latent space, and then they're used for their generative capabilities, similarly to GANs. But this is very important, is that the variational encoder is inherently continuous in its encoding. So we can identify a continuous parameter Z, ranging from 0 to 1, that is used to interpolate and generate unseen local domains, which are indeed the damaged lane marking in this case. So something that is in the middle between the two local domains that we train on. How does this work? Well, the working is pretty simple. Basically, we know that we have some kind of encoded representation of all the patches of our local domains. For instance, let's consider here the patch relative to the domain without marking, which for simplicity I put to everyone at 0, like a vector of 0. And let's suppose that we have a patch which is encompassing a perfect marking like this one, which has this hidden representation. what we do is simply performing a weighted sum. So in this case, we have a weighted sum, and the decoder representation will look like a damage marking, which is in the middle between the two. But another question is, why is this realistic? Like, why is this marking forcefully resembling real damage lane markings? Well, this is interpretable by thinking about the latent space interpretation of the variational encoder in the encoding of the local domains. So let's suppose that we have this latent space, which is learned by the variational encoder, and we have this patch-based local domain, which is encoded here in the middle. By nature, the variational encoder will try to encode these kind of perfect lane markings, which are extracted from the mask, in faraway points. So in this case, what we will have is that we will have some space between this local domain, which is in the middle, and these local domains, which are, let's say, these images in the local domain of markings, which are far away from it. But not all the markings in the example are the same. Like there could be, for example, cropped markings like this one, which are some kind of resembling both domains. So we have the perfect marking like this and an empty spot like this one. So what we are doing, interpolating in this case in the latent space, by passing our parameter z, is not only generating something which is continuous, it's also generating something that is realistic, because we are passing towards all these seen intermediate characteristics. So that being said, for the interpretation of the interpolation mechanism, here I'm going to present you the complete architecture about this. So we have the source domain, let's say the image pipeline, which is the one constituted by the GAN that is trained on local domains on images, and the one constituted by the variational encoder on the patches. We have 2 degrees of freedom, which is one is the interpolation parameter z that we have in the variational encoder, that is indeed to interpolate between local domains, and the other one is an additional interpolation parameter that is very simple. It's simply a blending, because working with masks here, we can simply multiply the absolute value of the mask with some kind of parameter which is between 0 and 1, and just blend the fake generated images with the original ones. That's it. I have to say that this pipeline is optional. Like the pipeline related to the mask interpolation with the variational encoder is not used in any in all of our experiments. But I mean, we propose that as an optional interpolation mechanism, which is based on this kind of mask-based interpolation. Okay, so now I presented you the method, and let's switch to the task that we face inside this, this paper. The first one is the lane degradation task. So the idea is to exploit the geometrical information about local domains in markings and asphalt in order to make images resemble ones without lane markings. For this training, we use the TuSimple dataset, which is just acquired in the US in highway scenarios, so it's a pretty restrictive dataset, and we use as the notation, as I showed you before, the lane marking binary mask. Also, very importantly, what we do is training only on 15 images. So again, we are very few shot in this kind of scenarios, and so we are building a method that can be used by just using a few images. We have another task that is the snow addition task. So again, the reasoning is that we have sidewalks in snowy scenarios which are not cleaned because cars are not passing on that. So on sidewalks, we will presumably find the snow. Instead, on the road, what happens is that cars are melting the snow. So at the end, we will have some kind of snow and non-snow pair that we can exploit in order to generate snow on the road in unseen scenarios. And for doing this, we use the ACDC snow subset, which is a recently came out data set, and the sidewalk and road annotation, again, with 15 images. We depart from autonomous driving by using the deblurring task. That is very important because we don't need any explicit annotation. So we just take the center of a foreground images of the Oxford flower dataset that we know being in focus. And we also crop the borders of the image that we know to be in the background, so out of focus. And we want to learn this kind of deblurring effect. These tasks can be used for transfer learning. So we also made experiments about transfer learning on this, like as a little spoiler. So let's first talk about the lane degradation task. On the left, you can find some input images, and here on the right, I'm showing you some output depending on our interpolation parameter Z. So in this case, you can see that our degradation of the lane marking is pretty realistic and pretty variegated, and of course is not linear. We have some kind of holes which are developing inside the markings, like this one that you can see here. So it's kind of resembling also how markings evolve in nature, like how markings are damaged by vehicles passing on them. We also evaluated this quantitatively, not only qualitatively, by comparing to baseline. So in this case, we select a pretty powerful baseline, which is called DLOW for interpolation. It's basically a generative adversarial network made for interpolation between domains. And as you can see here, it's managing to destroy the marking, but it's also changing the general color of the image. So we also improved the DLOW with our DLOW plus by imposing color consistency. So we basically have an additional loss on this. So here we are comparing with our result. So as you can see, we have 2 degrees of freedom instead of just 1, which is Z for the others. And as you can see, our interpolation is way better, so way more variegated. And also we have a way better color consistency of the patch that we are translating, because of course we are just working also using the mask. But as you can see, this is very realistic, and we also evaluated that quantitatively, comparing the generated damaged patches with real damaged patches by using some kind of other dataset and perceptual metrics like FID and the pips. And as you can see, our results like outperform the state of the art by a far margin, and we also ablate the importance of our blending mechanism with gamma. I also have some translation realism for the other tasks. So as you can see, for the snow addition one, we managed to transform original images by putting snow on the street, which is a very rare autonomous driving condition. So it's pretty difficult to collect, and we are able to generate them with only 15 images. And also here with the blurring task, I'm showing original images and deblurred one with some associated blurring mask, in focus mask, which are evaluated by using another method at the state of the art. So the whiter, the more in focus, and as you can see, our method is indeed producing in focus images that we also evaluate using the average of these maps. So we outperform the original images. Okay, so let's talk about the transfer learning, which is also the principal part. Our pipeline for transfer learning is very simple. So what we do is to augment images with our GAN and then submit that randomly to a task network that could be, for example, a lane detection network like this one. So we are randomized between the augmented images and the input one in order to increase variability. At the inference step, what we do is to infer on unseen scenarios like these ones, which are unstructured. So this one, for instance, has no lane markings, and we want to perform well on this. So let's talk about the lane detection challenging scenarios, which is the first transfer learning task. We compare against a source training, which only exploits 2 simple images, with our setup in which we exploit 2 simple and augmented 2 simple images with our system. We train 2 state-of-the-art lane detection system, which is our SCNN and RISA. And as you can see, we evaluate the performances on both 2 simple and IDD, which is another dataset acquired in India, which have damaged lane marking. So on Q simple compared to source, we don't lose much performances, so we are almost on par, while we outperform by a large margin the performances of the lane detection on the lane detectors on the IDD images without markings. And this is evaluable also qualitatively, as you can see here in the images, and in particular, look at this image where our lane detectors can be trained also to be resistant in this extreme scenario of a countryside road. We also experiment on semantic segmentation in snow, comparing by training semantic segmentation networks only on cityscapes images, which is a pretty famous data set, with our training in which we exploit cityscapes and an augmented cityscapes version with snow on the street. At the end, in this test, we test our systems on the ACDC snow dataset, which I have only indeed snowy scenes. And for doing this, we use 3 baselines, so DeepLab, D3+, PSANet, and OCRNet. So in this case, we evaluated that we increase the intersectional reunion of the 3 systems by like a fair margin, if you consider that we trained the system only by using 15 images. I'm talking about the augmentation one. And we also augment, we also increase the performances on road and sidewalk by a good margin in this case. As you can see, the injection of additional images is not only regularizing the road and the sidewalk, but also the general context understanding of the scene. For instance, you can see that in the non-training, this building, which is a class that we do not augment, is identified as struck, while our regularization strategy, by putting other images inside, makes the prediction better also on other classes. So I'm going to talk about one ablation study about the patch number that we can extract from images. So on 15 samples, we extract a different number of patches and evaluate the changes inside the performances as we did before with the patch degradation. So with GAN metrics, like pips and FID in this case, depending on the number of patches that you extract per image. So we can see that there is a strong dependence on the number of patches because of variability, of course. And we also compare this number with the number of samples to given a fixed number of patches that we extract. And as you can see, there is not much different, like there is no significant difference. So this is a call for being focused on what kind of information we can extract for images instead of just augmenting the number of images. Because of course, deep learning is becoming a lot data-driven, so we want to inject more human knowledge in that. And in particular to this task, I'm just going to give a perspective of what's beyond local domains, which is the idea of that. So we proposed a patch-based human interpretation of a problem by exploiting information like marking is near the asphalt, and we developed our local domain. But we can go further. So in terms of ideas, we can reason about information being in one data set, for instance, the fact that night is darker than day, and exploiting this kind of information. But also we can even go further and exploit dataset-based differences. For instance, the fact that fisheye distorts information. So to put inside, to generate relationships between different datasets. So this for us is also a call to exploit this kind of human knowledge machine learning, which is still underdeveloped in some scenarios like these ones. Thanks for your attention. I concluded my presentation. If you have any question, I will be here willing to answer. Thanks.